Guys, today we're going to be talking about diffraction. We've talked about reflection and refraction this week as two properties of waves. And so we're going to talk about diffraction today, which is a third property that waves exhibit. So I did things a little differently. I gave you some kind of fill-in notes. So you have most of the notes with just a few of the pictures missing and that sort of thing. I thought this would be more efficient. So some of these parts I'll be reading to you, but you have it there in front of you, but definitely write down all of the equations and what the different variables mean in the pictures and that sort of thing. So diffraction is the bending of waves around a barrier, and light exhibits properties of both waves and particles. So light can diffract. Light can bend around a barrier. So we'll talk more about the particle nature of light later when we get into quantum mechanics and that kind of stuff. But right now we're going to treat light just as if it was a wave. Okay. So when we have some sort of a barrier, okay, in this case we have two slits, kind of two openings. And if we have light that's coming in as a wave and it's being propagated through these two slits, then what happens is the light is going to move through the slits and then repropagate as if it was kind of like a brand new wave. So you're going to end up with basically wave fronts, not only from this single slit that it's coming through, but also from this slit. So it's going to look something like this. Okay, and what you end up with is interference. Okay, this wave that's propagating is interfering with these waves that are propagating. Okay, and so you end up with areas of constructive interference, okay, and areas of destructive interference. These would be like your constructive areas. Kind of hard to draw them. Constructive areas of interference and destructive areas of interference. Okay, and constructive areas of interference are going to correspond with a brighter kind of piece of light on whatever screen you have, and a destructive area is going to correspond with the light being dimmer at that point, not as bright. Okay, so we're going to discuss single, double, and multiple slit, also known as a diffraction grating. Diffraction grating. Multiple slit diffraction. Okay. And you can represent the light fringes and dark fringes on the screens in two different ways. Okay. Also, you can see, and let me go back to this part. You can see that the areas of constructive and destructive interference, this would be constructive, these would be destructive. Okay. And these areas are projected onto a screen or wall. The constructive areas on the screen are called bright fringes, and the areas of destructive are called dark fringes. Okay, areas where it's darker. All right, so we've got, let's pretend like we have double slit. Let's talk about that first. Okay, the distance from the middle of one slit to the middle of the next slit, okay, we're going to call that D. Okay, that's our distance between the slits. Okay, and this is our screen. Think of that as like the wall that you're projecting the interference patterns onto. It could be a wall, could be like a literal screen, just something you're projecting it onto. And that distance is length L, is given by a capital L. Okay. And what happens is, just like you saw up here in this picture, you end up with areas that are brighter, make those darker, and then you have destructive. So you have constructive interference, destructive, constructive, destructive. Okay, and it literally, so my pen making the darker lines, it's literally looks brighter. Okay, so that's one way to represent kind of the light and dark kind of areas. Okay, another way you can represent it is with kind of a graph of intensity, so that the taller the graph, the higher the amplitude of the graph, the greater the intensity of light. So constructive interference areas are going to have a really high peak, whereas destructive interference areas, the dark fringes, are going to have a very low peak. So the way it's going to look, and I need to turn my paper sideways because it's hard to draw it. The central max, the central maximum, central bright fringe here is always going to be larger, or the largest for double slit, and then the peaks are going to be just a little bit smaller for each subsequent bright fringe. So it's going to look something like that. Okay, so just make sure that the peaks line up with the bright fringes and the troughs kind of line up with the dark fringes, the areas of destructive interference. And this should line up, this central part right here, that should line up with this guy. So I'll just make this a little bit darker here. There we go. Okay. And once again, this kind of shows your intensity of light. So you have greatest intensity here at the center. Okay. All right. So we have, let me turn this back so you guys can see it. We have a maximum here. This is called the central maximum. Call it central max. And we also have max points here and here. Okay. Another one here and here where it's brightest. But then you also have some areas of destructive interference that are your mins. We're going to call those mins. Minimum, minimum, minimum. You guys get the picture. Min. Okay. And there should be a min here. Min on either side. Okay. And remember, those are areas of highest constructive interference. Constructive interference. And then the mins are destructive interference at the mins. Okay, so when we look at our equation, our diffraction equation's at the bottom. D is the distance between the slits from the middle to the middle. So distance between slits. This is the angle at which you're viewing it. Doesn't become so important because we're not going to use this equation a whole lot. But this is kind of the angle that you view the bright or dark spot through the slits. So the angle of viewing. This is our order number. M is our order number. Okay. Of the brighter or dim fringe or dim spot. Okay, we'll talk about more about that in just a second. M equals 0 or 1 or 1/2, 1 and 1/2, or so on and so forth. We'll talk about more about that in a minute. And that's from the central max. And then this is your wavelength of light that's going through your slits. Wavelength of light. Okay. So when we talk about double slit diffraction, the central max always has an order number of m equal to 0. And each subsequent bright fringe has an order number of integers. So the next max will be m equal to 1. The next max, m equal to 2. Okay. Arbitrarily, on the other side, these are still... This max would be m equal to 1, m equal to 2, but they give it just a negative value just because it's on the other side, So it really, your answers, you'll never have to worry about that negative sign. So what I'm going to do is leave it out because you're not going to have like a negative value for any of these things. So we're just going to say this is also equal to 1. This max is m equal to 2. And as you can see, the mins are going to be halfway between 0 and 1. So this max, the m for this min is 1/2. Okay, this min here is 1.5, right? Because it's between 1 and 2, 1.5. This one's going to be m equal to 2.5. You guys get the picture, and so on and so forth. So this one's going to be 1/2. This one's going to be 1.5. This one's going to be 2.5. Okay, and that's going to just allow us to do some calculations. So anytime we're dealing with light, okay, we can approximate that the angle at which you're viewing it, and that's the angle between the normal and like whatever fringe, is very small. Okay, we can approximate that for light, that it's very small when you're dealing with light. And so we have our small angle approximation equation. You're going to use this a lot more. Okay, both of these are on your equation sheet, but you're going to use this guy a lot more. Okay, and x is basically the distance just between subsequent slits, or I'm sorry, between subsequent maxes and mins. Okay, so just think of it as X is the distance between, like, say, the central region, you know, the central max, and whatever, you know, like, say I want to know, you know, what is the distance between the central max and the first, you know, the next max after that, like the next area of constructive interference after that, then X would be the distance between the central max and that next max. Okay, so it's basically the distance between your max, your central max, and whatever max or min you're looking, or min. You know, it's basically the distance between the central max and whatever max or min that you're referencing. You can't see that, sorry. So it's the distance between your central max and whatever max or min you're referencing. Okay, it's right here. Here's X. Okay, and these are all the same. This is your order number, just like before. M equal to 1/2. Okay, whatever. So for example, if I would have said, what is the distance to, you know, my next max, then that max is M equal to 1, so I'd put M equal to 1. This is your wavelength of light coming through the slits. This is the distance between the screen and the slits, and that's the distance between the slits, just like in the previous equation. Okay, so as a note, just remember that this equation can only be used with light diffraction, not sound, because sound does not create a small angle. Sound diffraction occurs over meters, not, you know, like millimeters and centimeters. We're talking about meters, because sound has such a longer wavelength than light does. So you cannot use the small angle approximation equation with sound. Okay, you can only use your main diffraction equation with sound. Okay, but you can use with light. You can use this with light. Okay, you can use this with light or sound. Okay. All right, flip the page. So that was double slit. I'll do an example in just a second. Single slit. All right, looks a lot the same. It's just a little bit different. Okay. Single slit diffraction occurs. So you might be wondering, well, how in the heck do you get interference patterns if you only have a single opening? Okay. Well, as the light travels through, believe it or not, light that is hitting on this side interferes with light that at a different angle that's hitting on this side, and you end up with interference patterns because of its wave-like properties. Okay, so, you know, here's your slit, here's your screen. It's the same, you know, this is going to be the distance between the slits here, D. You know, this is still your length L. Okay. The thing is with single slit is that you end up with a really bright central max, and then just you've got little maxes over here. So it's going to look something like that. And the light areas are the mins. So when you look at a graph of intensity, it's going to look like this. Kind of like that. It has a very large central maximum. That's indicative of single slit. So anytime you see that really large central maximum, okay, then you know that it's single slit. Okay, this whole thing is your central max. Okay, the way that changes things slightly, okay, is that before your M equal to 1, your order number equal to 1, remember, see, this is still M equal to 0, okay, but because the central max is so large, your M equal to 1 is actually going to fall at the area of destructive interference, at this min right here. Okay, this max should go right here. This min goes right here. So at this little minimum, like area of minimum brightness, this destructive interference area, okay, that order number is going to be M equal to 1. Okay, and then this next min is going to be M equal to 2, which means that this minimum here is M equal to 1. This minimum here is M equal to 2. These are mins. That's a min. That's a min. Okay, minimum area. So what that means for us is that the next order bright fringe, okay, this next order bright fringe here, that's the max, is going to be in between these two. So it's going to be m equal to 1 1/2. Okay, this max here, right here, it's going to be m equal to 1 1/2. This max here, 2 1/2. This max here, 2 1/2. Okay. All right, you guys get the idea. Okay. All right, so for single slit, the m equals 1 order number starts at the first minimum because that central max is so wide. Okay, versus for double slit, remember, the m equal to 1 actually started at the next bright fringe, not the dark fringe, because this is a smaller central max. Okay. Okay. All right, multiple slit diffraction is pretty easy. This is when you have a diffraction grating. A diffraction grating is when you have a ton of little slits, kind of like a CD. Okay, so you have a lot of little slits that the light has to travel through. Okay, on the order of, thousands per centimeter, thousands of slits per centimeter, and light is still coming in, right, this way, then you end up with a lot of interference patterns. Okay, the way the lines look different, so here's once again, remember D, the distance is the distance between the slits, these slits right here, and this would be length L. All right, this is your screen. You end up with basically symmetrical bright fringes that do not correspond. This is like a little illusion here. This doesn't quite correspond to, it looks like these are the same width and they're like totally not at all. Okay. Like for example, these are, like hundredths of a millimeter apart. Okay, these are like really close together on this side, on the slits. And these are like, half a meter, 5 or 6 centimeters apart. Okay, so these are like really close, and these are a little further apart, even though they look like they're the same. Okay, anyway, so you end up with these spikes that are symmetrical. Okay, and basically each spike corresponds to an area of constructive interference. Okay, central max, once again, is m equal to 0. The first order bright fringe is this is the max, m equal to 1, m equal to 2. So, note, multiple slit diffraction has the same order number distribution as double slit. So multiple slit and double slit are the same. Single slit's the one that's a little bit different. Okay? All right, let's do an example. All right, light of wavelength 5.8 times 10 to the 2 nanometers. Okay, is incident upon a slit of width, so it tells us the slit is of width, let's see, slit width, so D, 0.3 millimeters. Okay, the observing screen is placed 2 meters from the slit. Find the positions of the first dark fringes. So those are your areas of destructive interference. Okay, on either side of the central bright fringe, and find the width of the central bright fringe. Okay, so because we're talking about single slit, it's going to look like this. Okay. Okay. And so we're talking about, here's our central bright fringe. Remember, with single slit, because this is so large, your order number starts at the area of destructive interference, m equal to 1. And it wants to know basically the position from here to here, from the central bright fringe to the first dark fringe. Okay, and that's our x value. These are symmetrical. Each side, guys, on all of the diffraction grating patterns is symmetrical. So basically this distance, these are going to be equal to each of the dark fringes. Okay, so we're looking for x. So if we plug it into our equation, m lambda L over D. Our order number, because we're going to the first dark fringe, is going to be 1. M is going to be equal to 1. Lambda, this is going to be 580 nanometers. Guys, that's the same thing as 580 times 10 to the negative ninth meters. Got to remember that. Nano is 10 to the minus ninth. So it's going to be 1 times 580 times 10 to the minus ninth times the distance to the screen, which was 2 meters, divided by 0.3 millimeters is 1, 2, 3. It's 0.0003 meters. And plug that all in, and the distance between the dark fringe and the central max is, let's see, 0.0038 meters. Okay. Then it wants us to find the width of the bright fringe. Well, this is easy. Look, from this dark fringe to this dark fringe, that encompasses all of the bright fringe. So if this is symmetrical to this, all we have to do is double that number to find the distance of the width of the central bright fringe. So we're going to multiply that sucker by 2, and basically you get the bright fringe equal to, we'll see, I'll put this over here, 0.0077 meters. Ta-da! So that's the distance of the central bright fringe. Okay.